Hey, what's up? We're going to look at motion on an inclined plane. And from when I've taught physics, this has always been a topic that students have struggled with, but it's actually not that difficult. So you can see in this diagram, this is a typical scenario that you'll get given in the exam. We've got a slope, which has got an angle theta, and we've got a mass m, which is on this slope. We're going to look at the case where there's no friction to begin with. So the first step is always to label the forces that are acting on this. And the first force that you should always label is the weight, which always acts vertically downwards. Secondly, a really easy force to label is the normal contact force, N, and that's always at 90 degrees to the surface. So you can see there it's at 90 degrees to the slope. The problem with these two forces is that they're not really in the same line, they're not in line with each other, so we need to adjust one of them. We need to resolve one of the forces. And the one we're going to resolve is actually going to be the weight. The first step in any of these problems, step one, is to resolve the weight into two components, a component into the slope and a component down the slope, and it's the same every single time. And all you have to do the component into the slope is draw a little dotted line here. And just using basic geometry, we can actually prove that this angle here is also theta. So if the slope was at 30-degree angle, that angle there would also be 30 degrees. We're going to resolve the weight across this component, which gives us W cos theta, or mg cos theta, because weight is equal to mass times gravitational field strength. So there we have our component into the slope. So this is our component into. We now need to resolve our component down the slope. And there's a component of the weight, which is actually what makes the object accelerate down the slope. And this component here must be mg sine theta, or w sine theta if we're using the weight instead. So there we have our forces. We can now ignore this vertical weight. It's been resolved into these two components, into and down the slope. So we can look at this very simply. The object is not going into or off the slope, so the normal contact force must equal W cos theta. The force out of the slope is equal to the force into the slope, or N equals mg sine theta. So we've looked at this force and this force. Therefore, the resultant force, the unbalanced force, must be this one. The resultant force on this object is equal to W sine theta. Or we can say mg sine theta. We know that a resultant force causes acceleration using Newton's second law. Rf is equal to ma. So if we say mg sine theta, that's our resultant force, which is the component of the weight down the slope, is equal to ma. We can cancel off the m's, the mass doesn't have an effect, and we can write an expression for the acceleration of this object. A equals g sine theta. And it doesn't matter what mass object, that if you put an object on a slope, its acceleration will always be given by this expression in the case of no friction. So it's a very special case. So just to recap here what we've just done, we've resolved the weight into two components, the component into the slope and the component down the slope, and then we just use Newton's second law, the resultant force is equal to the mass times acceleration, to prove that acceleration is equal to g sine theta in the case where we have no friction. So in this example, we are now going to include friction. This ball is going to want to roll down the slope, so I've drawn friction acting going upwards. First step, we're going to resolve this weight we've seen here, where we've got our angle theta. So our component into the slope is given by mg cos theta, and our component of the weight down the slope is given by mg sine theta. There's two things that could be happening to this object. The first case is that this object is in equilibrium. That means this ball is not actually rolling down the slope, it's just staying where it is. In equilibrium means that the forces are balanced. So the force up the slope has got to equal the force down. So we can say that mg sine theta, this force, mg sine theta, the component of the weight down the slope, must be equal to the friction. So there we have an expression for those two. We can say that the force into the slope must equal the force out of the slope. So we can say that the normal contact force is equal to this component. So mg cos theta is equal to n. That's in the case of equilibrium where the forces are balanced. Often in real life, one of these forces will be bigger, and the ball is most likely to roll down the slope if there's not enough friction. So in the case here now, where mg sine theta is much bigger than the friction, the ball is going to roll down the slope. And we can use Newton's second law, Rf is equal to ma. So the resultant force in this case is going to be mg sine theta, but we have to take away the friction, because that's acting in the opposite direction as a vector, is equal to ma. And that's our expression which will enable us to calculate the acceleration of this ball down the slope. We still followed the same two steps. You resolve the weight into two components. One goes into the slope, and then one goes down the slope. And then we just use resultant force is equal to mass times acceleration to calculate the acceleration. A final example, just adding one more layer of complexity. This is like a car driving up a hill. So we've got a driving force this time, and friction is acting in the opposite way because this car is going up. We follow the same two steps. Step one, we resolve the weight. So we want to get rid of this weight here, and we've got an angle theta. So we've got mg cos theta, which is our component of the weight into the slope, and we also have mg sine theta acting down the slope, which is the same every single time. So if we were looking in equilibrium, which is where the car is moving at a constant velocity, or it's staying stationary, we'd say that all the forces are balanced. So the force up is equal to the force down the slope. So we could say that F plus mg sine theta, and I'll circle those two forces, must be equal to the driving force. And we can say that the force into the slope must equal the force out of the slope. So we can say that the normal contact force must be equal to mg cos theta. N is equal to mg cos theta. So that's the case of this object being in equilibrium. It's moving at a constant velocity, or it's stationary. Quite often though, we'll have a car that's accelerating up the slope. If it's accelerating up the slope, the driving force must be bigger. So we can use Newton's second law, Rf is equal to ma, and we can say that the driving force, take away the force down the slope, which is F plus mg sine theta, and I'll circle those two forces again, is equal to ma. And when you substitute in your values, you'll be able to calculate the acceleration. So, in summary, whenever you get an object on a slope, it's really, really simple. You follow two basic steps. Step one, resolve the weight into two components, into the slope and down the slope. Into the slope, it's always mg cos theta, and down the slope, it's mg sine theta. Then use Rf is equal to ma, or use the fact that forces are balanced to solve your problem. And just a key fact to remember, when there's no friction, the acceleration of an object is always given by a equals g sine theta, and you can see the derivation of that on the first slide. And that's it. Just follow those two steps. Thanks for listening. See you all soon.